Greetings. I'd like to welcome you today to a seminar titled Lidar Use in Smart Transportation, Vehicles, and Infrastructure. I'm pleased to be joined by Jason Marks, Autonomy Business Development Manager with National Instruments, and John Barad, Vice President of Business Development at Velodyne Lidar. Jason and John are experts in the field of technologies used by modern smart vehicles. Today's discussion will focus on the collection, analysis, and utilization of Lidar and scene data, as well as application to realistic modeling and simulation and hardware-in-the-loop applications. To begin, I'd like to thank the Mid-America Transportation Center, or MATSI, for hosting today's webinar. MATSI is the Region 7 USDOT University Transportation Research Center, with the headquarters located on the campus of the University of Nebraska-Lincoln. MATSI researchers collaborate with the USDOT to perform research related to MATSI's theme of improving safety and minimizing risk associated with increasing multimodal freight movements on the U.S. surface transportation system. The location of MATSI website is shown here. Please note that after the completion of the webinar, a recording of the presentation and summary materials can be found at the MATSI website. The collaborating universities of MATSI are shown here and consist of the University of Nebraska-Lincoln, University of Nebraska-Omaha, University of Nebraska Medical Center, University of Iowa, University of Kansas, University of Kansas Medical Center, Lincoln University, Nebraska Indian Community College, and the Missouri University of Science and Technology. Smart transportation systems are needed to address major safety concerns worldwide. In the U.S., there are approximately 35,000 deaths every year resulting from car crashes, in addition to approximately 100,000 severe or disabling injuries and billions of dollars lost in crash documentation, cleanup, lost wages, and emergency response service. For example, runoff road crashes with trees alone cost an estimated $1 billion out of the U.S. economy each year. Technology offers the opportunity to improve safety by keeping vehicles on the road and actively avoiding crash events through active braking assist, lane keeping, and blind spot warning. Connected and autonomous vehicles, or CAVs, pose an exciting opportunity to reduce the risk of on-road and run-off-road crashes using innovations in technology, mapping, simulation, and hardware-in-the-loop evaluation. Therefore, I am pleased to introduce our speakers to address these safety-critical topics. First, Mr. Jason Marks will discuss the role of instrumentation, sensors, and processing for smart vehicles and transportation. He will describe machine learning techniques for infinite space road mapping, simulation, and applications to hardware-in-the-loop technologies. Next, Mr. John Barad will discuss mobile and fixed LiDAR technologies and implementation, as well as their role in identifying road users, mapping movements, and developing informational systems for vehicle-to-everything, or V2X, technology. With no further ado, I present Mr. Jason Marks. Thank you, Jason. You may share your screen when you are ready. You are good to go, Jason. Thank you very much.
Excellent. Well, thanks for having me. I'm excited to talk to you guys about autonomous vehicles, autonomous systems. When we talk about the safety case for autonomous vehicles or advanced driver assistance systems, we often talk about how do we prove safety. One of the clear ways in which we prove safety is going to be on how we actually test the autonomous systems themselves. And what's different from autonomous systems than many other in-vehicle systems that we've tested in the past is that we have non-heuristic algorithms being deployed for perceiving the world. And we're going to be talking about ways in which we can leverage technology and technological advancements and certain strategies to actually address those particular challenges around testing those non-heuristic algorithms. So I'm calling this topic Testing Machine Learning in Autonomous Vehicles. This pertains also to advanced driver assistance systems, and we will talk about that at length here. So in general, I'll start this conversation around what constitutes machine learning in autonomous vehicles, what parts of the autonomous vehicle software stack are using machine learning. Then we'll talk about the approaches to actually test those machine learning based systems. We'll talk about the challenges of one of the major pieces of test, which is simulation. I'm sure you all have seen plenty of videos of simulated autonomous systems. We'll talk about a couple of the major challenges and areas of research for that type of simulation. Then we'll talk about test strategies that the automotive industry already employs namely software in the loop and hardware in the loop, and how that workflow pertains to autonomous systems. We'll conclude on some types of on-road testing as well. So for machine learning in autonomous vehicles, just kind of opening it up, many of you have probably seen some permutation of this type of slide before, where what constitutes an autonomous vehicle or an ADAS system usually constitutes some compute system, whether that's centralized or decentralized. Connected to that compute system is a number of sensors that perceive the world. Those sensors usually consist of Lidar, light detection and ranging. John will talk about that at length after me. Radar, which is electromagnetic spectrum from 77 gigahertz or 76 to 81 gigahertz. Camera-based systems, stereo vision or single point camera systems, area scan cameras, as well as GPS or regular GNSS and other methodologies for localization of the world, including IMU, wheel speed sensors, and things like that. Inside of that autonomous compute hardware is actually just your standard robotics paradigm, which really goes through the process of perceiving the world, planning on what to do, and then controlling action of the vehicle. So into the autonomous system is a number of sensors we just described, and output is the control of the vehicle, namely brakes, throttle, and steering. And if we take a look and open up that box and look at the software stack that is inside of that, you'll see some permutation of this kind of paradigm. So the sensors usually for perception are camera, radar, Lidar, and then a number of other sensors also used for localization of the vehicle in the world. Inside of the perception stack, or software, is a number of machine learning algorithms that are actually non-heuristic. They use deep learning or other types of AI to determine where the vehicle is, to determine the scene it's looking at, lane markings, object detection, and things, and estimation of where that object's going. The then planning stack of that constitutes mostly heuristic algorithms, but also potentially some machine learning algorithms. Like particularly when we talk about behavior selection, there is a large number of choices that can be made in any given situation, and then there's an optimization to be made. That can be done either heuristically or non-heuristically. As we get into the control system, that's where we see FPGAs deployed for deterministic control. Namely, we pick a trajectory from the planning stage and we then drive it through steering, throttle, braking, or gear shifting. And those usually are actually constituted drive-by-wire commands over the CAN bus. I did want to talk briefly around the topic of machine learning in perception systems, because this is where the majority of the machine learning occurs. So one thing to note is that there is no set methodology for determining how you perceive the world, how you classify the world. There's tons of different strategies, and everybody's deploying something slightly different or potentially majorly different. One such example, and this picture is taken from Berkeley Deep Drive, is that if you have your sensor input of Lidar and camera, if you wanted to have an accurate view of the world, you could fuse those together in the beginning. You could overlay your point cloud on top of a camera image and then send that through a convolution and send that through a bunch of deep learning algorithms and determine what that classification could be. That's one way of doing that. We call that early fusion. However, you could just as well send both the camera data and the Lidar data through two separate convolutions and two separate deep neural networks to classify the world. And then you could then compare the outputs. We call that late fusion. Both are equally viable, and they both net you potentially different results. So you have a lot of options for what you could be doing here for perception systems, which makes this problem even more challenging because there's no set agreement upon the algorithms you would be using for this. So with that said, I hope I kind of made you understand that machine learning is complicated. There's a lot of different permutations of it, but there's lots of ways that which we can actually approach validation of those machine learning systems. So there's kind of two different approaches we talk about when we talk about validating machine learning. We talk about white box validation and we talk about black box validation. White box validation really means in my deep neural net, are my nodes activating? And that's because you have the vision to look into the box and say, are my nodes activating? Is that an activation occurring? That's one way to validate that. Black box validation really means I am looking at a black box machine learning algorithm and I only have access to inputs and outputs. How do I validate a system that I only have access to inputs and outputs if I can't look at what's going on inside of here? Most of what we're going to be describing today is actually going to be on that black box category. So when we talk about testing machine learning, one thing that I'm not sure it will surprise you or not, but 99.9% of the validation that occurs for machine learning algorithms in autonomous systems occurs in simulation. And the reason that is because of that quote unquote infinite state space that occurs in the autonomous vehicle space. You could have any permutation of road conditions, of weather conditions, of vehicles, of actors moving in various ways. So even if you encounter a scenario like that in real life, you can imagine that there's an infinite number of permutations of that scenario you could have encountered in real life, which is why we simulate it. So we do 99.9% of the testing in simulation. And then once we're confident in simulation, what we do is we move a subset of that simulation to actually deploying those simulations in a hardware environment. So we deploy the algorithms that we're testing in simulation to a piece of hardware, and we stream that information to that hardware. And we call that hardware in the loop test. And then we do a combination of data of on-road testing as well as data recording of those on-road vehicles. I will say that the on-road testing can go either direction. It can happen at the end when you want to validate that everything is safe, that you've already created a great system, or it can happen at the beginning when you just want to aggregate a bunch of data so you can then play that back into a testing scenario. So data recording happens in both stages. So because 99.9% of the testing happens in simulation, let's talk about what are some of the really big challenges of simulation. So what makes simulation hard? Why are we not just all doing the same simulations? Are we all not having the same simulator that we're using? Well, the real answer is I like to kind of group them into three different categories. There may be more, there may be less. I like to talk about it in three main categories. One is that when you do simulation, you're actually trying to replicate what that particular sensor on the real vehicle would be seeing. And you want to do that to a realistic way that can actually train and test the algorithms that are being deployed. So in order to do that, you have to have a high enough fidelity of the sensor you are modeling that actually is representative of real life. And that is very hard to do. Just like anything else in academic world where you're trying to model a physical phenomenon with math and physics, you can get to a pretty good confidence that you're there. And then there's always some different permutations that occur based on environmental conditions, things like that, that diverge from the perfect physics-based implementation of that. Just that same thing occurs for sensor models. You need not only a physics-based implementation of that sensor model that represents how that sensor looks, but you need to validate it against an actual sensor so you know that you're getting a correlated sensor capability. All right, the second one is that, as you might imagine, the more and more computation you spend to create a high fidelity sensor, the more processing power you're taking up on your computer that's generating that sensor model, and therefore the hit on bandwidth you're going to get and actually generation of those sensor models. Because not only do those sensor models need to be very realistic, they need to be updated at frame rates representative of how those real sensors will act in real life. So if you have 16 cameras, 16 radar, 16 Lidar, you imagine that that's taking up a ton of computation to make sure that they're accurate. And on top of that, they need to not only be accurate, but be updating at a rate that's at or faster than real time so that you can actually get a testing scenario to occur. And then the last, and the virtually impossible thing to address right now, a lot of major research is going into this, is test coverage. So as you might imagine, we just talked about the infinite state space that occurs in the autonomous world. Well, how do you, even with one scenario, define where the limits of test coverage are? There's a lot of research going into that, a lot of great companies doing great work on figuring out what to test and how to test it. But again, an infinite state space makes it very hard to test. And this is the limiting factor mostly as to why autonomous vehicles aren't on the road right now. So we don't have a good way to say, have I covered enough scenarios? Have I covered the majority of the scenarios to know that my system's going to act as I expect it to act in a real world environment to some level of safety? So talking real quick about the architecture of simulation. All simulators will look something like this. It's not, there may be some variations of it, but it will all look something like this. There will be a simulator that has a world environment in it. A lot of people are leveraging Unreal Engine 4 for that. Some people do not use gaming engines for that. But that is where the ego vehicle, which is the vehicle under test, is driving in a simulated real world. And there are actors, so other vehicles, pedestrians, cyclists in the world that are navigating around that. Those all have to have some level of intelligence so that they interact with the vehicle appropriately. From that simulation world, you would attach sensors, those sensor models, to that ego vehicle, and they would be looking out at the world in the appropriate location for that world. And they would be streaming that sensor information that's supposed to be representative of that real sensor to the system under test. So if you're testing just the perception systems, what you would be doing is you'd be streaming a high fidelity version of those sensors to that perception system. That perception system would do its classification of the world, and it would output to either the planning system or back to your test system. Here's what I think I'm seeing in the world. If you wanted to validate just the perception system, what you would have to do is then compare that output from the perception stack to the semantic information. And because you're using a digital world, a simulated world, you have access to the ground truth associated with that world, and that's how you can validate the perception outputs. Likewise, if you want to do a full stack test, what you would be doing is you'd be outputting the sensor models, the high fidelity sensor models, to the perception stack in the control system, and then you would have the perception stack output its outputs of where it thinks everything in the world is to the planning system. Planning system would decide where to drive the vehicle. The control system would output commands and drive-by-wire to the commands, and you would output that back into your simulator. Inside of that simulator, you would then have to have a model of the vehicle dynamics occurring for that vehicle, so you accurately drive that vehicle and close the loop. And thus that occurs at a high frame rate. Oftentimes we're seeing frame rates around 30 frames per second for these type of activities. So talking specifically about the challenge of a sensor model fidelity. So not only do you need a physics-based implementation of radar, LiDAR, camera, ultrasonic, yada, yada, yada down the line, but you also need the equivalent ground truth of that if you're going to validate the perception system. So if you're implementing radar, you need the correct representation of that millimeter wave signal, but you also need the appropriate object list per point, so you know that you're actually getting that correct. Same thing with LiDAR. If LiDAR, you're generating a series of points in space, and you need the physics-based implementation of that points in space, that can be fairly challenging to do, and I think John will talk about that a little bit, but light and millimeter wave for radar, they have all sorts of characteristics that are pertinent to the material properties that you're reflecting off of and things like that, but you need an implementation of that, and then you need the equivalent semantic information. So for LiDAR in general, so for example, we actually use a per point semantic information. So we categorize each point that the LiDAR is shooting out and what it constitutes as its real life answer. That's a bush, that's a tree, that's the road, that's the lane paint, that is a car. We classify that. So you may be asking, why can't I just use an idealized version of those sensors? Why do I have to have a physics-based implementation of those sensors? That seems computationally expensive. Well, the example I like to use is that if we look at the previous Tesla crash, there's actually, we've had two more since then. We've had the one, I think that just occurred this week, and then the one that happened in Taiwan a couple weeks ago. If we look at the one that occurred in Highway 101 where they ran into a fire truck, and again, I don't work for Tesla, this is just a speculation as to what occurred, please don't quote me on that, but what we believe is that part of what happened was the radar that Tesla was using was shooting out at the fire truck, and amongst other things. And there were things like cones in the road and things in the road that were very small in comparison to the fire truck. Well, the fire truck was reflecting so much electromagnetic reflection because it's so large and it's a metal object that it was actually washing out in the signal to noise ratio in the electromagnetic spectrum anything that would be telling the vehicle, you need to change lanes and avoid this truck. So what would have potentially prevented that is if in simulation we would have adequately modeled that radar so that we're actually getting the signal to noise ratio to know that it's not able to detect small objects in the road. It can only detect these large objects because it's washing out in the signal to noise ratio. Likewise, we might be getting a lot of interference from multipath elements of radar. We might be reflecting off of certain objects back into the radar receive chain on the vehicle, and that would prevent us from actually getting an accurate representation of what that what the real life is. So all those type of things you need to be able to model in such a way that's representative of real life. Signal to noise ratio, the number of antenna elements, the reflectivity of the objects, any type of, for LiDAR in particular, any type of speckle or turbulence for rain. Those things need to be modeled so you adequately address the capability of that particular sensor. So with that said, now you believe me, hopefully, that we need to have a real life implementation, a physics-based implementation that's validated for those sensor models. Well, how do we actually then go about taking it to the next level, making sure that that sensor is representative of what a real sensor is? Well, there are a lot of different methodologies, and I'll just mention a few of them. But in particular, I'll cover a couple here, is some people actually, beyond just implementing the physics of those sensors, they actually use real data of a particular sensor and then train it using machine learning to actually represent that model in its digital environment. Many people go out and take expensive equipment to various materials and categorize the reflectivity at various wavelengths or at various electromagnetic frequencies. Some people actually get those sensor models from the vendor directly. Some people buy a bunch of sensors and back engineer them. And some people actually take chambered measurements of various sensors over the air to make sure that they're getting a representation of what those sensors are. So there's all sorts of methodologies. They all have validity to them. And I think some combination of all of them will ultimately prove both the most accurate and the lowest computationally expensive to actually do this in real time. So once you've got the sensor models adequately modeled, you've got your simulator set up in such a way that will let you run it in real time and test the particular pieces of your control system that you want to test. Now it's your job to address the infinite state space. And you can do that a number of ways. One such way that almost everybody implements is to parameterize their simulations in such a way. One such parameter I'm showing right here is of weather parameters. But you can imagine that this is just a one parameter that's variable. You could have an infinite number of parameters that are variable, but you need to define what those are and you need to define the state space you're acting in. One way to actually scale this is to deploy to the cloud. And this is where we see the Waymos of the world that say they've tested over 100 million miles every year, close to 1 billion miles every year. They're able to do that because they parameterize their simulations. They deploy them typically to Dockerized containers using Kubernetes, and then they execute these simulations massively in parallel, tens of thousands of simulations at any given time running on cloud servers. So the other piece of this that I haven't quite talked about is what happens when you want to simulate something you encountered in real life. You recorded a real life example and you want to then play it back and you want to then vary the parameters of that thing you encountered in real life. One such way to do that is to create a digital twin. There's a couple of companies, one of which that we partner with as well, that are very good at taking real life recorded data and converting it into a digital twin. So I'll go ahead and play this video so you can see. On the top side is an actual drive in Austin, Texas of you're seeing a camera version of this. And then we send that up to the cloud through a series of machine learning algorithms that's able to classify the world and effectively recreate that entire scene in a digital twin environment. So below you're actually seeing a simulated version of that. What you'll see is that the landscape's different, the cars are different in the other one because we drop in just a different set of vehicles. But what we're doing is we're actually replaying and recreating a digital twin of that drive. This is really important for a number of different reasons. One is because you can now test what you've encountered in real life and vary the parameters of what you've encountered in real life. And the other is actually a little bit more nuanced, and that is it provides a methodology for validating a real version of a sensor in a digital world. So you could effectively do exactly what I'm showing here, put a Velodyne Lidar on the top of this vehicle on the top, and take a bunch of measurements, create a digital version of that Velodyne Lidar on the other system, and then tune that sensor model to make sure that you're getting a 100% correlation between the two in a digital world. All right, so that's an introduction to software in the loop, because that does constitute software in the loop and simulation. I often use interchangeably. Simulation can test both the entire software stack or a particular model or algorithm. We call that model in the loop. But I'll talk about how that goes from that software in the loop to ultimately to hardware in the loop. And hardware in the loop, despite it constituting only a small portion of the actual number of tests being conducted, it's still a necessary piece of validation at OEMs to actually feel that they're safe in deploying this, because there are certain phenomena that occur in the real hardware that you're deploying these algorithms to that may not occur in software. Thermal components, these hardware is optimized for actually deployment. So you may encounter different phenomena actually going through those particular network interfaces with computational kind of optimizations and thermal optimizations that occur there. So that whole workflow kind of looks like this. You do the software in the loop, the simulation side of things, you validate the hardware, you feel good about the hardware that you've created, then you deploy that software that you've created to that hardware, and you do that hardware in the loop simulation using that same kind of description for software in the loop simulation that we've described earlier, and then you eventually deploy it to a production test environment and ship it into the vehicle. So when we talk about hardware in the loop, we can talk about a number of things. You have all sorts of options as to where you quote unquote draw the line for the hardware. You could theoretically emulate targets over the air for the images by putting a big screen in front of cameras, or radar by putting an electromagnetic target generator in front of a radar, or LiDAR that has a bunch of ways in which that people believe you can do that as well. You could go what we call behind the sensor, where you're injecting still into the sensor, but digitally. But what's most common in a hardware in the loop environment for testing the ECU, the electronic control unit that's deployed the perception systems, is to inject into the network bus directly. So network buses for sensors vary. For example, for camera, we use something called a SerDes interface that is either from, typically right now, GM, or sorry, from Maxim or from TI, so it's GMSL or FPD-Link. For LiDAR, we see a lot of different Ethernet kind of technologies being used. Right now, I think the push in the industry is to move to automotive Ethernet. So we call that 100 or 1000 base T1 as the right Ethernet protocol, two-wire Ethernet protocol. And then for radar, we see a lot of people using CAN or CAN-FD. But that is the network interface you have to inject those simulated sensors into in order to test the ECU. So what that looks like is you take that same simulated test drive environment that we described, you convert that into the appropriate network interface in a deterministic manner, and then you inject that into the ECU under test. And then you wait for a response from that ECU. That ECU responds with usually CAN drive-by-wire signals. You send that back into the digital converter box, and that then streams that information back into your virtual test drive environment. And that's how you do a hardware in the loop test. Now, these hardware in the loop tests can get massive. Like if you walk into some OEMs, you may see entire rooms constituting one hardware in the loop test of one ECU. And the reason they do that is because there's so many different facets of the ADAS system. There's radar, LiDAR, camera, there's brakes, there's steering, there's driving. So you need some methodology to emulate each of one of those things. And that could take up a ton of space in order to actually get those accurately emulated. So that's the hardware in the loop system. As I mentioned previously, the last piece of this is that there are road tests that occur as well. So the road tests occur in two different spaces. They occur either at the beginning when you don't have an autonomous system active, you just want to record what's going on in the world so you can then play that back or convert it into a simulation. So that is what we call in-vehicle recording. That occurs usually without the autonomous system active. Then there is the final road test where the autonomous vehicle system is active and you want to make sure that it makes the right decisions in various scenarios. So here's an example, and let me make sure that this plays without sound. Good. This is an example from Milbrook, which is a test facility that actually does conduct ADAS testing. And this is actually when you've deployed that ECU to that software to that ECU, so you can see how the vehicle reacts in various situations. You may have seen a video, I think that got virally popular, of kind of the pedestrian crossing the road and a vehicle just smashing into that pedestrian. That's obviously what we don't want to happen. That's why we test it on the road. All right. So a couple of challenges I'll just mention real quick around in-vehicle data logging or in-vehicle recording is that, particularly for cameras, you have a ton of data. I'll use this, for example, one OEM we work with has 16 cameras, up to 8 megapixel resolution, up to 30 or even 60 frames per second, some with extremely wide field of view with fisheye lenses. As you might imagine, that ends up being gigabytes per second of data being transferred. And if you're recording for hours at a time, you could very quickly get to the terabytes of data. And that's where we're talking about how do you store that in the vehicle? You usually have to do that through a series of RAID arrays. And how do you extract that from the vehicle? Every time you can't just plug in an Ethernet cable and stream that data to a network. You have to have an IT infrastructure ways that can do 100 or 400 gigabits per second of streaming, or pop out those RAID drives and put them elsewhere. Because every time you take a vehicle down, you're wasting money. those vehicles need to be operating, recording information in real as much as possible, so you get the maximum uptime. They need to be able to take that data off as quickly as possible. Once that data is off, now you got to move that around in the cloud or wherever it needs to go. That's a whole nother challenge. And then the piece that really gets people down, and the thing that people spend the most money on, is how do they annotate that data? By annotation, what usually happens is data is sent off and to a warehouse of people that sit there and they draw bounding boxes around different classifiers and say, this is a person, this is a vehicle. And they do that frame by frame. And that could cost you millions of dollars for one set of data to be recorded. There's a lot of people that are investing in technology to do automation of that annotation. But you need to be confident in that data you're annotating, because that's going to be treated as the ground truth for what you're doing. So if you're not confident, then you're not going to get good ground truth. You're not going to get good training data. You're not going to get good testing data. It's all a big challenge around data. So wrapping up here, there are a ton of challenges for testing autonomous systems, and there's not good answers to every single one of those challenges. We have theories as to how you can do it, but there's a lot of research that still needs to happen in order to get where we need to be confident in the safety of systems. And a lot of that is because there's no way to look into the algorithms that are being deployed for perception systems. So if I were to impart some wisdom or advice onto the academics in the room right now, I said, spend a lot of time and energy trying to solve these really hard problems. Things like the sensor model fidelity, things like optimizations of those sensor models, and things like how do we address test coverage. So we really need breakthroughs in particular around how we address test coverage in order to solve this problem. And I will say that once we get some of those breakthroughs through, it will streamline the ability to get to that autonomous future that we all want to believe is possible. Hopefully I covered a good amount of information on the strategies that people currently use for ADAS and autonomy to validate them. But please, I'm going to open up the floor now. I think we're at a good time for questions. So let me know what you have.
Very good. Thank you very much, Jason. We had a couple of questions come through on the chat. First question was asked is, are the software or hardware in the loop currently commercially available?
Yes, they are currently commercially available. Everyone's kind of in their infancy, so it's a learning phase for a lot of companies. National Instruments does deploy to OEMs and tier ones for ADAS and autonomous hardware in the loop solutions and software in the loop solutions.
Very good. And where would people go to find those commercially available solutions?
Usually websites. I'm a great contact if you're curious what NI is doing, but also there's a number of our competitors in the space that are equally viable that you could reach out to them. But happy to be the first point of contact for anybody curious about that.
Very good. And I will post at the very end of this meeting my contact information. I can serve as a liaison to direct traffic to you, Jason, or you are also welcome to post your contact information in the chat for anybody who wants to reach out to Jason then. Second question that was asked is, how are the weather and ambient environmental conditions modeled in your simulation?
Good. A number of different ways. I mean, so if you're using a game engine, usually there are some meshes that are equivalent to, that let you kind of drag and drop in weather conditions. But there's also a lot of other research going into weather modeling. So some people, because really the weather itself is not what's important. What's really important is how that weather affects the sensors. So the things like wetness on the lens, that's something that really needs to be modeled accurately, because that's an effect that will really have a dramatic impact on the perception systems. Likewise, if you're using rain or snow, you may actually get turbulent effects for certain types of LiDAR over the air that would have a really interesting effect on how that point cloud looks. Whether rain doesn't have a significant effect on radar systems, but it can have effect on the reflectivity of various objects if there's water on them. So that's really what you care about, more so than what you care about how the physically rain in simulator looks like.
Very good. And another question was posed in the chat is, can we use augmented reality or AR techniques for making decisions about surrounding traffic instead of running simulations themselves?
I may need a little bit more depth on that question. What type of techniques for AR are we considering?
Augmented reality and some of those techniques implement simulated vehicles or simulated aspects within a realistic ambient environment that isn't a digitally recreated environment.
So in that kind of sense, there's a couple of good, Oxbotica, for example, a couple of other companies that are working very heavily on taking playback data and adding things like, how do I add another vehicle to that playback data? Or how do I change what that vehicle is seeing in real time? A lot of AI implementations are using that type of, how do I change what's being played back into my system to actually to modify what you're seeing. So that's great for if you have a scenario that you've already recorded that you want to then vary to parameterize. What that doesn't do is generate a synthetic scenario from scratch.
Another question posed in the chat, a great question. Has anyone simulated what happens to the physical sensors, including or such as the radar and Lidar, when any other car on the road has a similar degree of emission? Does that increase the unintentional interference?
That's a great question. And there's a lot of technology actually going into radar to try to block out how the interference between multiple different radar. We do that through something we call multipath, where we put a different radar in another vehicle and it's bounced off of a variety of objects and sent back into the receive chain. And that shows up as noise or even pretty high noise in some cases that will wash out the ADC in various scenarios. So that's how we approach that. But there's certainly a lot of research happening in that. We know particular technology companies that actually equip highways with electromagnetic receivers to try to figure out how much actual spectrum is being shared at 77 gigahertz for radar in today's kind of ADAS world. So great question and a great research area to go into. Also, I will note that there are radar companies that are trying to deploy things like channel state information on your radar, similarly to how like LTE and Wi-Fi technology work right now, to actually discern that the radar response you're getting for that particular radar pertains to the radar that it was sending out.
That very much goes to a follow-on question regarding whether or not there's some point of saturation with CAVs, at which point the interference becomes too high to detect or overcome.
Yeah, I mean, it's always a possibility now. Things like, everybody has a cell phone right now, and that cell phone is being transmitted all the time. So how do we have LTE spectrum not being washed out in your receive chain of your cell phone? Well, in the same way we do it people theorize that you could do it in a vehicle. You could send channel state information. You could have a preamble in your radar to say, this is what my radar is. So we can only look for that and lock into it. A lot of, a lot of the beamforming technologies being used in radar do a really good job of pointing beams in a specific direction, which helps a lot with that signal to noise ratio and washing out.
Very good. Do you have any information, ideas for sensors or processing paradigms to advance modeling beyond controlled highway applications such as well-paved roads, excellent signage, good roadsides, and into more rural areas where the road may have deteriorated quality, there may be heavy encroachment of roadside near to the roadways?
Yeah, great question. So we, in our partnership with MonoDrive as a simulation company, we used road deterioration, sign deterioration as parameters that you can vary. But I will take it one step further and say there are a number of autonomous applications that are more closer to real life happening today in off-highway applications. So if you think about mining trucks in Western Australia, for example, Caterpillar is very vocal about their deployments of those. You have to simulate not only this like a deteriorated road, but you have to simulate the gravel, the mine, maybe poor visibility, dusty scenarios. That makes it significantly harder, and you have to have an accurate simulation of that capability. Likewise, you have a bunch of American off-road vehicle companies that are building tractors and combines and things like that. And there you have to simulate things like high crops and how those react and how you would simulate, how you would perceive those with sensors. So those are very hard challenges. But everyone has a theory about how to kind of address those. We have our theory, but it may or may not prove to be sufficient.
Very good. We do have a handful of additional questions. However, I'm going to delay those until the second part of the open forum. I have recorded those. But with that, we'll go ahead and begin to make a transition over to John. Thank you very much, Jason.
Thank you.
With that, we will introduce Mr. John Barad. John, you are also welcome now to begin to share your screen, and John will be discussing the role of LiDAR with smart transportation, specifically with respect to the infrastructure and use of LiDAR on fixed points.
Great, thanks, Cody. Yeah, let me pull up my screen here. Let me know when that comes through.
You are good to go.
All right. Well, thank you. Thanks, Jason. That was a great talk, and I think it's it's wonderful to see the role of simulation. A lot of our customers utilize simulation for a number of applications, and so again, my name is John Barad. I'm the Vice President of Business Development at Velodyne, and I focus on partnerships and developing strategies for new markets that utilize LiDAR, because there are many that are growing. But real quick, it's interesting to to share a little bit about the history of Velodyne, because it's a good story and kind of sets the context of what we're about as a company and an industry. The company was founded in 1983 by David Hall, who really invented, he's a brilliant mind, invented high dynamic range subwoofer for Velodyne Acoustics, which is still around today, create very high quality subwoofers and speakers. As the company grew, David continued to invent until in 2004, DARPA came out with the grand challenge of asking companies to figure out how to cross the Mojave Desert with an autonomous vehicle. And in 2004, he entered the race with the camera technology. Here's a little picture of what the first truck looked like, but sadly did not complete the race, nor did anybody that year. Came back the next year, and this is when he invented the real-time 3D LiDAR, or the rotating LiDAR as we know it today. You can see a picture of the first LiDAR there. He did finish the race, actually lent the design to a few other teams that also finished the race, and thus began the autonomous vehicle industry. A couple years later, we began commercially selling LiDAR with our first, the HDL64. It's kind of the iconic LiDAR, and today we continue to be a leader in the world of LiDAR and innovating new types of sensors for not only autonomous vehicles, but for a number of different industries. We have offices all over the world, and we work with really every major auto OEM and others. But just so it sounds like it's a pretty technical bunch, so I won't necessarily need to dig into the definition, but LiDAR essentially is hundreds of thousands or millions of points of light. For those that don't really understand it too well, these points of light are emitted into the world, and the time it takes for the reflection to come back to the sensor is a measurement distance that we can then use to create a 3D model of the environment. Here's an example of a raw point cloud. We use all of our sensors use 905 nanometer lasers. We have multiple lasers, anywhere from 16 to 128 channels. And this is an example I'll show you. Here is an actual video. This is a video of our Alpha Prime. This is our 128 channel LiDAR. It is the most advanced LiDAR in the world today. It has a 245 meter range. What you're seeing here is, this is the raw point cloud. It's a 3D model that you can move around in. It's created in real time. The different colors that you're seeing are the different reflective intensities from the lasers. There is a and you can make out you know, all the objects. You can make out the lines in the street. You can even, at this point here in the video, it's really fun. You can actually see the graffiti on the side of that truck there. There's just so much concentrated light that's focused. You can see the street signs. Those tend to be orange or red because they're higher reflective materials. Make out and even make out people. So this is the sensor that's driving the autonomous vehicle industry, but it's not our only sensor, and it's there's different types of sensors for different types of projects and different types of needs. It all depends on what the application is, and we've got a wide family of sensors, from our Alpha Prime, which you just saw. We have the Ultra Puck and the Puck are both rotating LiDAR. The Ultra Puck has a 32 channel LiDAR and the Puck is a 16 channel LiDAR. And the Velodyne, which is our new directional based LiDAR, which is exciting and being used to be integrated into vehicles behind the windshield or in the bumper, and has a lot of great capability. I won't go through this list, but I wanted to share that a little bit about each one of these sensors in case there was some interest, and I'm happy to talk about more individually. But there's different ranges, there's different resolutions, there's different channel counts, different fields of view. So all projects have different needs and support different products, and so our goal is to create a real wide variety. And what that is doing to the industry, which is exciting, is it's creating this really just broad, vast ecosystem of exciting applications and exciting industries that are popping up. As LiDAR matures, it becomes more robust, it becomes smaller in size, it becomes lower in cost. We have wider variety of different sensors, as I mentioned, and really you can create a lot of really exciting applications. And so I wanted to share with you this little video that we just put out. It's called, this is the Automated with Velodyne ecosystem. And the Automated with Velodyne program is a partner program that we have developed. Hopefully that's not too loud for people. But we've developed a way to interact and help promote our partners and help establish a conversation in this industry. There's so many different projects that are utilizing LiDAR today, from automotive applications, security applications, smart city applications, drone applications, that there's a lot of commonalities, a lot of learnings between these companies and these industries. And so we're really helping to drive and bring together different uses, exciting innovations that are enabling new ways of doing business, new efficiencies, better safety. It's exciting. Even agriculture, this is a company that is an orchard sprayer. Here is a company out of China that's doing a street sweeping application. It's really exciting. Oops. Oh, sorry about that.
John, I think we've lost the audio.
That's the audio. Sorry about that. Well, yeah, I'll pause there. You know, can you guys still hear me? Okay.
Yes, we can.
Okay. It changed my headset. These AirPods don't last very long, and that must have screwed up the video. But you know, it's exciting to see all those applications, and hopefully it gives you some ideas of some areas, you know, that are where people are innovating and where there's exciting work that's going on. But it's not always about putting LiDAR on a moving vehicle. You know, as you saw from the video, there's a few in there that I'll talk through now, where we're using LiDAR in a fixed position. It's still capturing and creating a 3D map of the environment, much the same way that it is on a autonomous vehicle, but we're using it instead for perhaps analytical purposes or security purposes, or even just monitoring people flow and traffic flow in an intersection or along a highway. And so, you know, and the attributes of LiDAR really lend itself to these types of initiatives. Here's an example with a company called Seoul Robotics. We're working with them out of South Korea, where we're using LiDAR to track and monitor this crowded intersection, where we've created a virtual boundary around the intersection, and we're tracking and counting each individual pedestrian that goes through the intersection. They're red if they're in the intersection, they're green if they're outside the intersection. We're counting them, we're tracking their speed, their location, their direction, their trajectory. All these different attributes really allow us to be able to understand what is going on in that intersection at any given time. And you know, it's not only about efficiency, but it's also about safety, and safety is really what drives us, and what we're trying to really help promote in the industry. You know, there's so many pedestrian fatalities. Just here in the U.S. alone, 6,500. It's growing. You know, as people are more distracted behind the wheel, it becomes a problem. And majority of them are happening at night. This is some data taken from a recent AAA study that shows the current ADAS platforms, ADAS solutions for pedestrian automatic emergency braking systems in 4 vehicles. And AAA tested this, and I think Jason alluded to, you know, these cars that crash into those dummies. Was probably taken from this test. But as you can see, you know, these current systems, which are just using camera and radar, really failed miserably. No one really does well in necessarily in any category, besides the one green category, adult pedestrian or crosswalk for the Toyota Camry. But as you can see, you know, turning right with a pedestrian or night pedestrian and crosswalk, you know, those are examples where there's just the technology that is currently in use is just not working. And I think it's because, as you can see from this spider chart, the overlap in different capabilities of LiDAR, radar, and cameras, you know, they don't perfectly overlap. And that's why a lot of OEMs that we're working with utilize these 3 sensors together, because it creates good redundancy. These different sensor modalities can help improve upon weaknesses of other sensor types. You know, radar doesn't necessarily have great resolution, but can be used in night conditions. Cameras have great resolution, but obviously, you know, don't work well in night conditions. LiDAR, on the other hand, does have you know, good. It works in all lighting conditions. It does have great field of view. You know, it has good range, and certainly, depending on your application, you know, there's you know, these different types of sensor suites can be leveraged. At night, you can see a little image of a LiDAR looking at a vehicle from behind versus a camera, and very clear to see the differences. One of the interesting aspects that's really starting to take shape is the idea of privacy. Just actually last week, I think it was, there's a bicameral bill that was introduced in Congress called the Facial Recognition and Biometric Technology Moratorium Act of 2020. This is, the idea that the misuse of facial recognition technology by police departments has gotten a lot of attention for obvious reasons. Microsoft, IBM, Amazon stopped selling their facial recognition technology, and as we think about a world where we want these analytics, we need this data of intersections, within airports, on roadways, to help improve safety, help improve efficiency. We do have to be mindful that there is a concern with cameras and the use of them for interfering in people's privacy. But LiDAR does not, even though we can detect people, but we can't identify them. We don't identify their skin color, their eye color, or any of their personal features, as you can see here. So there's a lot of interest in LiDAR from that perspective. And in Montreal, we're working with a company called Blue City Technology. We've got a couple deployments throughout Canada and in the US where we put LiDAR on a light pole, and we're using the LiDAR to monitor vehicles for speed and to estimate their speed, their trajectory. We detect and count vehicles, classify vehicles and trucks and people and bicyclists. And you can really detect and do this in very crowded environments. Here's an example of a Blue City implementation in Montreal. Just very simply, just to introduce you to it, very simply, just counting the number of people or vehicles that go through the crosswalk or go through the intersection. You can see this is a lot less resolution than some of the other examples I showed you, because this particular example is using a 16-channel LiDAR. And even with a 16-channel LiDAR, even though you can't see too much with the naked eye, the software is still able to identify, classify the different points that hit the target and be able to determine what sort of object it is. When you take it a step further into kind of a multimodal type of implementation where we're classifying different objects and monitoring them, you can see the analytics that come out of this type of scene are just really stunning. We've got the pedestrians in green. If there's a red dot, that means there's a pedestrian in the crosswalk. Blue are vehicles, and you can determine which direction they're going, what speed they're headed, if they're making a turn or not. And this can be used to time traffic lights. It can be used to ensure that the crosswalks are of the appropriate length. It can be ensure that if there is an accident, that it's detected. And when you compare it to other technologies, LiDAR, in the past, people have thought LiDAR is expensive. Well, it's not so much anymore. It's a mature technology. The price has certainly come down, and when you factor in all the other components required to create a system, you still have quite a cost-effective system. So this is a slide from Blue City Technology again, where their entire system, a LiDAR-based system, is less than $15,000 per implementation for an intersection, where you really only need one sensor, versus an inductive loop system. You have to dig up the street. You got to put one in each lane. it's quite a high installation and maintenance cost. Radar doesn't necessarily, you need multiple radars. You don't necessarily get the resolution needed to really do a lot of the classification that you would want, or the multimodal application. And cameras, certainly, on a sensor to sensor cost comparison, cameras can be cheaper, but multiple cameras, more compute hardware is typically required in order to really achieve what you want. So it certainly is, we're kind of at the outset where it's a business case is certainly feasible to be made to begin to leverage LiDAR. And this is happening all over the world. In Australia, we're working with a company called OmniAware, who is developed, this is an example of some tests we've done with the government of Victoria in Australia, where, as you can see, LiDAR detects something in the road. It's monitoring an intersection, something small that maybe people in a vehicle haven't been able to see, and you can see that information can be sent to the vehicle for a V2X application, where LiDAR can continuously monitor an intersection that may be miles away from a particular vehicle that doesn't have the line of sight to be able to see it, and help reroute traffic to improve that. In France, we're working with a company called Parameterizing, which is doing, they mostly do speed control systems. They've deployed hundreds of speed control systems. If you've ever driven in Europe, you see these on the side of the highways, and they're getting more sophisticated. It's not just a camera and a radar, but LiDAR is being implemented now, because LiDAR is able to provide more resolution so that you can distinguish what lane the car is in, that is speeding, or where the infraction is coming from. It can be from both directions, so you can actually measure multiple cars at multiple times. You can even, in one instance here, identify cars that are too close together, if there is poor driving behavior, and be able to detect that. So LiDAR gives more resolution than what a radar has in the past, and I guess it's good news for speed traps, bad news for those that have fast cars. At the University of Nevada in Reno, we're working with those guys there. They've developed, and they're one of the leaders in the space here, developed a smart corridor, or developing a smart corridor, where they've deployed LiDAR at, I think it's 9 different intersections now, in Reno, near the university, and they are monitoring all the same types of use cases: monitoring traffic, monitoring pedestrian flow, trying to study the traffic, make sure that they can improve throughput, and assess how certain times of the day there are spikes, and why that is, because you can get really good resolution. And in addition, they're using LiDAR to detect wildlife that are going over crossings. So certainly, that's a big budget item for the U.S. government, certainly to build these expensive overpasses for wildlife, and it's not always necessarily clear how well they get used. Radar is useful, but doesn't have the resolution to really count, how the animals are crossing, or what animals are crossing, and so LiDAR can be effective here, not only for counting the crossings, but also to detect if there are animals on the road, to create early warning signs for vehicles. From a kind of a different infrastructure standpoint, not necessarily vehicle infrastructure, but at airports, obviously that is another very crowded, trafficked environment. And so LiDAR being used in a variety of ways to monitor people as they flow through an airport, monitor security lines to ensure that they're not too crowded, or in this day and age, even that they're monitoring for social distancing effectively, and that it's there is better good controls for people to have overflow areas or abilities to move around. There even is company Outsite is working with their first installation is at Charles de Gaulle in Paris. They're even implementing and connecting fever detection systems. So not necessarily just regular RGB cameras or radar, but you can detect, you can combine other types of sensors with LiDAR. And here in an airport, you can imagine all these exciting use cases or interesting use cases, from monitoring trolleys to seat occupancy to the bags are coming in the luggage area. And so I guess I know I'm coming up on time, but just a couple more interesting use cases that we're seeing is pedestrian monitoring. This is a pedestrian mall in Japan. We're working with some folks there as to ensure that people are adequately monitor and analyze, so that the malls can assess where the crowds are at any given point in case there's an emergency, but also helps them understand how people use and congregate in the area. And on the security side, LiDAR is being used to monitor for these. It's being used in Europe at a nuclear energy facility, nuclear power plant, and you can use it very effectively to monitor boundaries. Just as we saw when you're monitoring people in a crosswalk, you can use a LiDAR to create a volumetric perimeter, if you will, and determine somebody inside versus outside. This is a company called TacticAware that you can see these little. This is actually a simulated environment that they take video imaging and LiDAR imaging and combine it to create a 3D world where people can be tracked in real time. And the LiDAR actually controls the camera and the direction of the camera, so that you can get a visual on people if that's necessary. So that's my time. I appreciate it. I'm sorry if I went a few minutes over, but certainly feel free to reach out and we can answer some questions here. And thanks for listening.
All right, very good, John. We had a few questions come in the chat.
Wonderful.
I would say first question that I wanted to address: are you using LiDAR with camera paired, or are your systems primarily LiDAR based without a camera application?
Yeah, so as I mentioned earlier, there's a wide variety. So it depends on the solution that you're trying to build, whether that is a solution where a camera would be needed, like the last security solution that I showed you, where it's nice to have a visual that a human can look at and analyze. But even in the Blue City case, it's just the LiDAR, and that's all that's necessary, because what you're after in essence is when you create a 3D model, this 3D model with the point cloud with the LiDAR, you're really wanting to know the XYZ coordinates of everything in that scene so that you can track it and use it to time the stoplight. And so camera is not necessary in that particular application.
Very much dovetailing to that were two related questions. The first of which is when you're conducting tracking of pedestrians or vehicles, that's obviously a time-based event because LiDAR is going to produce your point cloud. How do you stitch together consecutive point clouds to do tracking?
Yeah, so and that's the wonderful thing about LiDAR is that it's actually a lot simpler to stitch together multiple sensors. So you can create, when you're creating a 3D model, and you can really bring together dozens of sensors to create a 3D model of the entire space. And I've seen implementations where there have been I think upwards of a dozen or so sensors all connected to one PC or to one server itself. But in the airport example, the Lidar is being implemented all over, and you can connect to all of them. And it's a little bit different type of scenario or paradigm than what you're used to with cameras, moving from one scene to another. But now with Lidar, you can kind of create this virtual world, if you will, that can seamlessly be viewed from one sensor to another.
And with respect to the Lidar itself, do you know of any potential vulnerabilities or hacks that would render the Lidar either less effective or render it incapacitated? We're specifically looking at potentially blocking or jamming or frequency directed right at the sensor.
There certainly is. We've got interference mitigation capabilities within our sensors, so that it goes to the other question maybe that was asked during Jason's presentation, that other sensors or our own sensors won't interfere with each other. I think the sensors work in all lighting conditions, so bright sunlight or complete darkness. But it is light. I guess the best way to interfere with a sensor is just to block the line of sight. It's like a camera. If there's no line of sight to the object, you can't necessarily see it. But there are, I guess, other materials that do reflect differently than others, and so that's another area where that you can get some noise from a particularly dark object or a hyper reflective object.
For applications that might be critical security, for example, if you're doing pedestrian or vehicle tracking around secure facility federal buildings, for example, and are there applications by which bad actors could introduce artificial noise into these Lidar, which might render them less effective? Are you aware of any applications that have been tried to date?
No, I'm not aware of any of that, but I'll have to talk with my technical team. I'm sorry, I'm not aware of any.
And there are already radar being used in vehicles. We are well aware you showed some excellent video from Lidar used with vehicles. Are there any applications by which radar might be better suited for some applications than Lidar itself?
Well, like I said, I don't think it's there's no one example of sensor that will do it all. They're not Swiss Army knives. I think that there are applications where Lidar is more effective. There are applications where radar cameras can be more effective, certainly. I think it depends on what you're trying to do. To be frank, there's a lot of different types of each of those sensors as well. There's ultra long range Lidar. There's as I showed you, there's multiple different types of Lidar. There's ultra long radar, I should say, as well. So it depends on what you're trying to do. Typically what we focus on at Velodyne is I guess it's not short range necessarily, although our sensors do detect very short range. But we have maximum ranges of 100 to 250 meters. So kind of within those that area is kind of where our sweet spot is. But it's kind of a hard question because there's so many different use cases where radar can be very effective, and is today very effective for certain types of applications.
Thank you very much, John. And so now we're going to move into the final phase of this webinar, in which the audience is welcome to solicit and pose questions to either John or Jason. If you have anything you would prefer to speak out loud, feel free to unmute yourself. We did have one question come in, Jason, before that we didn't have time to answer. And that had to deal with integrating driver behavior into the simulations. How do you address variations in driver behavior when you're addressing your simulations?
Great question. So we call that actor intelligence. There's a number of ways to do that. In a playback example, where you are playing back what you've already encountered in real life, or a scenario that's defined by the Euro NCAP, what you can do is set waypoints for a actor to interact with the world. And then you can set some type of intelligence on top of those waypoints and say, I want you to be aggressive in sticking to these waypoints, or I want you to be very passive in interacting with how me as the ego vehicle kind of interacts with you. There's a lot of people that are actually building out some pretty intelligent software stacks on their actors to have some type of interaction that's supposed to be indicative of different types of drivers and different types of different areas of the world. For example, your New York driver may act significantly different than your driver in, Alabama.
I've never heard of anyone complaining about New York drivers before. How would you deal with potentially multi-vehicle uses in roadway applications? For example, would any systems that are out there support agricultural vehicle integration, bicycles and motorcycles?
Yes, absolutely. That's critical for agricultural applications, your John Deere's, your C&H's, your Caterpillars of the world. They're building autonomy into all their vehicles moving forward. It's even interesting that the 5 levels of autonomy that we talk about for on-road vehicles is significantly different for off-road vehicles as well. But the ways in which they validate them are very similar. I think there was actually 2 parts of that question, if I heard correctly. How do you deal with multiple vehicles interacting with one another when they all have some level of intelligence? We call that multi-ego type applications, where that's actually a fairly novel way to kind of approach the problem, where say you're doing 2 vehicles have some type of level of autonomy, and you need to figure out, not only predict where that vehicle will go, but kind of understand how that autonomy interacts with one another. That way you might actually use one simulation environment with 2 ego vehicles acting in it. Very cool application that people have deployed. There's other cool applications though that maybe also kind of pertain to that, where the infrastructure in a parking garage, for example, might control where vehicles go. So you want the communication to occur between that parking garage intelligence and telling those vehicles where to go. So lots of kind of, I'm not sure if I answered the question appropriately, but it's all good applications, and then people have all tried to do something in those areas.
I think that's very good information. Now, with respect to John, when you're looking at timing for signalization, you had mentioned potentially only using 1 LiDAR per intersection. Is it possible that the nature of these single point intersection maps can be used for traffic mapping in a city? For example,
absolutely. Yeah, absolutely. I think it's certainly possible to have one LiDAR per intersection. It depends on how big the intersection is. We see anywhere from 1 to 2, or if there's depending on how many lanes there are. But yeah, I think certainly having the ability to have those fixed solutions to map and monitor the traffic in real time at multiple intersections is really, I mean, that's kind of what University of Nevada has been doing, is having these multiple intersections with LiDAR so that they can monitor traffic in real time, help develop certain real-time maps that are a bit higher resolution than what road sensors could offer of traffic patterns and where there are blockages and issues.
This question would then be raised to both of you. How close to real-time processing do you have to have in order to facilitate sensors and V2X interactions?
I'll go first on that one. So it really depends on the application space. So if you are doing a purely software simulated application, you may be able to get away with slower than real time, and you maybe even want faster than real time because you want to run more simulations in a certain period of time and a certain number of machines you're running. So how close to real time do you have to be? The answer is it depends. If you're using it in a real deployment, or for hardware in the loop, you want to be very accurate to real time because you want to know exactly how that hardware is going to interact at real time in its current processing capability. On road, you're obviously going to want to act in real time as well. And the question, how it interacts with V2X. So V2X is just another piece of the pie you're going to have to simulate. And again, it's going to depend on the application at hand.
Yeah, well said. I think it's the processing requirements for multiple sensors and collecting all this data. It can be processed in real time, and certainly there is that capability. I mean, just as a car operates itself in real time, it's making decisions in real time as to what obstacles to avoid and where to go. An intersection, an infrastructure can do the same. There's a component though about having that infrastructure in place and having the connectivity to the vehicles and the applications within the vehicles to be able to receive that information in real time. And I guess that's a different piece of the puzzle. Maybe we need somebody from 5G world to chat with us, be on maybe the next webinar or something.
I will say that there's another element of real-time nature that a lot of people discuss in this world, and that's determinism. So how much jitter you have in between two steps in the pie. Where that really matters is if you're doing types of things that require really accurate timing information from multiple different domains. That's where you would need very low jitter in order to actually correlate them appropriately in the right timestamp.
Very good. So we'll look for any final questions, but the one last question that I had potentially for Jason to answer, and this could be very well addressed by John too, is can the LiDAR and V2X and simulation-based processing, can that ever be streamlined into an on-vehicle application wherein the one vehicle results can collaborate with the second vehicle's results in real time?
There's plenty of people that have thought about that use case, and it certainly is an option. I think that you may, if you were to pose that to people that are developing autonomous vehicles right now, they would probably tell you the problem at hand is hard enough as is.
Yeah, I mean, I'd say, from a, it's certainly possible. I think, we're starting to see applications pop up with in the HD mapping world where cars are roaming around and mapping the streets, and that information that they collect, they're not just mapping, the streets, but they're mapping oftentimes the best lanes to be traveling in, or the best routes to use, or where there is an accident or isn't an accident. That information that a car is capturing certainly can be leveraged by other vehicles if they're connected, to a central service that's able to share that information between vehicles, so that if you're where I'm from in San Francisco Bay Area, if you're traveling down to Silicon Valley from San Francisco, you'll be able to know which lane is faster on the highway versus just more generically looking at Google Maps and seeing which street is faster. You can really get some hyper accurate models for you.
Well, thank you both, John and Jason. I appreciate your time very much, and for the audience for listening. So as we wrap up and conclude this seminar, I would like to point your attention to a subsequent seminar to be held next week on July 8th between 4 and 5 Eastern Standard Time, which will host Miss Amanda Ham from Virginia Department of Transportation, also as the head of the Connected Vehicles, the Connected and Autonomous Vehicles Pooled Fund Program, as well as Fahad Shuja with the Ontario Good Roads Association and one of the principal players of Macavo up in Ontario. We're talking about the role of government and data sharing in policy and their connection with connected and autonomous vehicles. So you're welcome to attend next week. Note that this slide deck will be made available online shortly. as well as the seminar. I thank you all for your attention. I do appreciate the kind of responses and questions from all the audience, and I hope that you found this presentation and webinar to be helpful.
Thanks, everybody.
Thanks, guys. Take it easy.